In Chapter 3, we start off with some basic concepts of probability and counting. There are some definitions at the beginning. Read through those examples. Let me know if you have questions about any of the definitions. Um, this little example here kind of sums up the beginning definitions. If we're rolling a dice, that's our experiment. We're trying to see what's going to happen when we roll the dice. The sample space, that means all the possible outcomes. So if you're familiar with the dice, there's 6 numbers, there's 6 possible outcomes. An event is some subset of this sample space that we may be looking at. For example, we want to roll an even number for some game. That's the object. Well, an event could be then rolling a 2, 4, or 6. And an outcome then is just when you actually do roll the dice, you conduct the experiment, what occurs. So if you roll the dice and get a 2, that's your outcome. And a crucial concept is the fundamental counting principle. The word fundamental kind of implies that it's pretty important. It says if we're doing events, 2 separate events, there's a certain number of ways to do the first one and a certain number of ways to do the second. And we want to know how many total ways those 2 events could happen, all the different possibilities. We can count that just by doing the number of ways of the first event multiplied by the number of ways of the second event. And it's going to make a lot more sense looking at an example. And let's go to let's start with this one. How many ways are there? How many different types of cars are there? And so you have 3 events here. One is picking a manufacturer, one's going to be picking a car size, and then one's going to be picking the car color. So how many total ways are there to choose from this? Well, you can see it in a tree diagram. There would be 3 different manufacturers we're picking from, and each of those are split into 2 sizes for their car, and then each type of size of the car comes in the 4 colors. So if you counted all of these possibilities at the bottom, there's 24. The faster way to get to that is say, okay, there's 3 choices for the first decision. There's 2 choices then for the size. So 3 times 2 gives me 6 nodes at this level. And then there's 4 choices for the color. So if I take those 6 nodes and multiply them all by 4, now I have 24 total outcomes. So there's 24 different ways to pick your manufacturer, car, size, and color if these are your choices. Here we're entering a PIN, another example with the fundamental counting principle, and it's going to be 4 digits long. How many access codes are there if each digit can only be used once and not repeated? Or number 2, each digit can be repeated. So in Excel, or anytime you're trying to figure this out, fundamental counting principle, think of the choices you have to make. Here we're entering 4 numbers. If the digits cannot be repeated, we're going to have 10 choices for the first number, 0 through 9. There's 10 digits to push in. Now we can't repeat, so there's only 9 left for the second digit, 8 for the next one, and 7 for the next because we can't repeat. So we can do just the fundamental counting principle says to multiply those together, and that gives us how many total options there are for this PIN number. Now, if you could repeat, it's just you have 10 choices for every single digit because you can use the same digit over and over again. So that gives you 10,000 options if you're allowed to repeat. So now looking at probability, we're going to look at 3 types. Subjective we won't use very often, and that's like predicting the winner of a sporting event. You can base it off of some stuff that you know, who's on which team, how well they've done, but it's really kind of subjective, and still there's a lot of chance involved, and it's not a precise science. The other 2 types we'll use quite a bit in this class, especially empirical, or another word for that is statistical probability, so we'll use that. The first one we're looking at is classical probability, and you're just going to have to count here. So the number of ways something can occur divided by the total possible outcomes. That's the probability of the event occurring. So a simple example with dice, there's 6 total possible outcomes. So the bottom number is 6. What's the chances you roll a 3? That's going to be 1 out of 6. And you could write that as a decimal as well. So that's the probability of getting a 6. The chances of getting a 7, well, there are no 7. So that's 0 out of 6. So we're just counting here how many ways it can occur on top, total number of possibilities on bottom. Rolling a number less than 5, so count how many numbers are less than 5. There's 4 of them, so it's 4 out of 6, which is 2/3, or as a decimal, right there. So going back to this example, what's the chances that you randomly guess someone's PIN number? Well, pins, you can repeat numbers for most pins, so there's 10,000 total possibilities. Only one of them is correct, so the chances that you randomly guess someone's PIN number is 1 out of 10,000. Which is a very small chance. So the next type of probability is based upon statistics. So if we gather a bunch of statistics, we can then calculate the probability of events. And you're going to notice this looks pretty similar to what we just looked at, but it's going to be based off the statistics we gathered. So we're going to look at the total frequency of whatever we're gathering information about, and then on top, it's the frequency of that specific thing we're looking at. Again, that's a lot clearer with an example. Let's say we have asked 2,451 people some survey question, and here's the responses. So that total frequency is how many total there are. If we want to know what's the probability that some random person says always, it's how often that event happens out of the total number that we've gathered statistics about. So the probability somebody says always, we would just look at our stats and find the number of ways that occurs over the total. So statistical probability is only as good as the stats you have, and basically the law of large numbers says the more stats you gather, the more data we have, then our statistical probability is going to actually get close to the true or the theoretical probability. Basically, the more stats you have, the more accurate your probability. Because if you think of theoretical probability, stuff like rolling a dice, that's very precise. You have a 1 out of 6 chance of getting a 5 when you roll. The chances that someone says always to that survey we just looked at, well, if we've only surveyed a few people, our data might be off. But as we continue to survey more and more and more people, we're going to get a really precise probability for that situation. And I've actually done this in class before when I'm in front of a classroom. Tossing a coin, if you personally just toss a coin 10 times, you may get something like 7 heads and 3 tails. So it's not close to 50-50. But if you have everybody in the class do it 10 times and put all their numbers together, as you get more and more coin tosses put together, it's almost always really, really, really close to 50-50. Because as you add more and more data, that the statistical probability gets really, really close to the actual probability of the event. One thing everyone should be aware of, probability has to be between 0 and 1. So it's got to be a decimal between 0 and 1. 0% means it's impossible to happen. 1 or 100% means it's guaranteed to happen. So you have to be somewhere in between there. If your calculation for a probability ever comes out to something bigger than 1 or something negative, you know there was an error somewhere along the way. It's got to be between 0 and 1. And the complement of an event is all the outcomes from the sample space that aren't in the event you're looking at. So if we call the event E, we denote the complement just with an E and then a tick mark. If we call the event A, we would do A and a tick mark. A tick mark means the complement. So it's red E prime means the complement. And here's an example from rolling dice. If what you want is a number at least 5, that would be a 5 and a 6. So the complement of that is everything else from the sample space, which would be the 1, 2, or 3, or 4 on the dice. And so a key thing about probabilities and complements is they always add up to 100% or 1. If you think about getting a 5 or a 6, that has a 2 out of 6 chance, and this has a 4 out of 6 chance. So 2/6 plus 4/6 equals 6/6 or 1. I like to also just throw the weather example out here. If there is a 60% chance of rain, the complement of rain would be no rain. And so 60% chance of rain means a 40% chance of no rain. An event in this complement always adds up to 100%. So looking at conditional probability, it's the situation we're trying to calculate the probability of something happen under certain conditions. And the condition is that another event has already occurred. We write it like this in mathematics, and we read it, the probability that B happens given that we know A, given A, has already occurred. First example, I'll just look at a deck of cards. There's 52 cards in a deck. What's the probability that the second card you draw, if we're drawing 2 cards, is a queen, given that the first card is a king? So we drew a king out. What's the probability we get a queen on the second deck? Well, there's 4 queens total, and because that first event already occurred, drawing the king, now there's only 51 cards in the deck. So the probability of getting a queen, given that we drew a king, is 4 out of 51. If we don't have that conditional probability, just in general, the probability of getting a queen is 4 out of 52. But drawing that king changed the game up because now there's 1 less card in the deck. So let's look at some conditional probabilities from a table. Here's information on men and women and whether they like chocolate or vanilla ice cream better. What's the probability that a randomly selected person likes vanilla? Well, do probabilities the same way we have been doing. The number on top is what we're looking for. How many people like vanilla? 137. And the number on bottom is how many total possibilities are there? 287. So that's how you get the probability that someone likes vanilla. That's not a conditional probability. It's just asking about vanilla. Now, the conditional probabilities are usually given away by the word given if they're written out. So given that we randomly select a male, what's the probability they like vanilla? So the key here is that we're given we have a male. So stop looking at this entire chart and just look at the male column. Bring that over here. So if we're just looking at the male, we know we have a male. What's the probability they like vanilla? Well, I should probably bring these over too so we can see it. The probability they like vanilla is 76 out of the 142. So what we've done is we've changed our numbers here because we're only looking at the male column. Given that a randomly selected person likes vanilla, so another conditional probability here, what is the probability that they are male? So again, I'm only going to look at what I know I have. I know I have someone who likes vanilla, so I'm only looking at this row. Well, out of this row, what are the chances that they are male? Well, there's 76 males in that row out of a total of 137 people who like vanilla. So that's the probability we have for that situation. And the final definition I want to look at in this video is independent and dependent events. So independent things have no effect on each other. The occurrence of one does not affect the probability of the other. Dependent events do affect each other. So there's some examples down here. What do you think? Smoking a pack of cigarettes every day and developing emphysema or lung disease, are those independent or dependent? So they're probably dependent events. Doing one, smoking the cigarettes, will affect your chances, your probability of getting chronic lung disease. What about tossing a coin? After you've tossed the coin and got head, does that affect your probability on the next toss? If you've got 10 heads in a row, does that affect your probability of getting a tail on the next toss? And no, it doesn't. Those are independent events. No matter what, each time you toss a coin, the next coin flip's probability is still 50% heads, 50% tails. And here are the formulas we would use mathematically to prove whether events truly are independent or not. Because sometimes it may seem that they should affect each other, but we want to know for sure, so we crunch the numbers. So if the probability of B, given that A happens, is still the same as the probability of B was before, then the events are independent. So looking back here, the probability of liking vanilla and the probability of being male, those are dependent because the probability of liking vanilla was right here, but it changed once we were given that the person was male.